Daniel So. Daniel's a new faculty member at the OSC. I think you joined officially 3 weeks ago.
Yeah.
2 weeks ago. So for the last 14 years, he's been a member of the technical staff at Sandia. He's done a great deal of research, varying from sort of nonlinear optics to 2D materials, to atom interferometry, quantum communication. 20 years ago, though, he got his start working with high-power fiber lasers as a PhD student at the University of Southampton, which I'm told is the mecca for fiber lasers. He went on to apply his trade in Silicon Valley in a startup company where he was an R&D manager, and also went on to large corporations like JSU before going back, or going for the first time to Sandia. We're here today, however, because I guess roughly halfway through his career at Sandia, Daniel came to a revelation, which I think all of us have for at least a short moment in our lives, that his true calling in life was to be a quantum physicist. For most of us, lasts maybe a couple hours. Daniel was able to convince his employers at Sandia to send him back to graduate school at Stanford. He became a PhD student again 10 years later in the group of Hideo Noguchi, studying nonlinear quantum optics and 2D materials. He also developed one of the first squeeze light sources at Stanford. And I would just say, as an experimentalist in quantum optics, this is one of the noblest pursuits as an experimentalist, and one of the most treacherous pursuits. Took that back to Sandia, developed a squeeze light source there, and I think a lot of what we'll hear about today is based on most of his theoretical ideas and his experimental prowess in squeeze light interferometry. Thank you very much.
All right, thank you. Thank you very much for a generous introduction, and I'm so moved. Yeah, so thank you so much. I'm very glad to see you all, and this is one of my dream jobs, to really teach here and work together with every one of you here. And I really thank God for that, and I really expect a lot of productive collaboration with every one of you. So thank you for this opportunity. So today I'm going to talk about a little bit different thing that I did for job interview and job talk, which was more focused on the quantum systems and network and those kind of things. But today I'm going to talk about my passion on the squeeze light and quantum materials. So it's two-part. One is the quantum super resolution imaging with squeeze light, which is now hot topic, and everybody claims to be doing the same thing. And then please pay attention. Which part is different from others? So you need attention. And the second part is about the single photon absorption using some novel materials. Okay. So light is a harmonic oscillator, and many of you will object to this, and I know that. So it's very difficult to grasp that light is actually a harmonic oscillator, like a particle. And so far so good. So many evidence support this hypothesis, and I still call it hypothesis until it is proved wrong. Okay, so Hamiltonian is typical harmonic oscillator, and we have position and momentum. And then now, remarkably, there is something called the coherent quantum state of light. That is an eigenstate of the annihilation operator A, which is the very closest thing to actually a physical system called laser light. So laser light is close to being a coherent state. And because of the uncertainty principle between the position and momentum equivalent Q and P operators here, so if we put the light state on a phase space like Q and P space, then you will always have uncertainty, non-zero uncertainty in measurement of Q value and measurement of P value. And because of this Hamiltonian, it ever rotates around the origin. And imagine that you're going to measure Q value using some novel operators called homodyne detector. then you will always have some kind of uncertainty in measured value because the Q value is not a single number, and it is kind of statistical number, and therefore, if you keep measuring Q value, then you will see a lot of uncertainties while the average rotates around the circle. So that's the coherent state. Now, I will start talking about the squeeze light. So what is squeeze light? For that, one of the best ways to describe squeezing operator. So I will demonstrate that squeezing operator does an amazing thing, and it manifests itself in the measurement. And this is so far conceptual thing only, but you will see that this squeezing operator will be in action soon. So squeezing operator is a very weird thing called an exponential of some combination of annihilation squared and creation squared. And one of the things that squeezing operator does on our usual annihilation operator and the creation operator is to transform this into an interesting combination of those two. And the other day, my student Sid came to me and showed that this is related to the matrix singular value decomposition. So he's brilliant, and some of you will understand what I mean. So this transformation is interesting since if you do the similar transformation for Q value, Q operator, and P operator, which is actually measurable. So we cannot measure A or A dagger, but we can measure P and Q because they are Hermitian operators. And then you see that using very simple operators, so addition of these two to add them together, and you are left with e to the minus r factor in front, and the new q prime becomes q times e to the minus r, which is basically a scaling of q, and p does the opposite. So basically, if you just subtract these two, then you have the p times e to the plus r. So now, what it implies is that the uncertainty on Q becomes smaller if R is positive, and uncertainty on P becomes larger if R is positive. So that's a very interesting transformation, and what it does is exactly this. So basically, the light is now ellipse instead of the circle, because there is an unbalance between delta Q and delta P, and then it ever rotates again. So if you try to measure Q value, for example, then delta Q changes over time. Sometimes delta Q becomes very narrow. Sometimes delta Q becomes very wide. And therefore, this is the measurement result of delta Q over time. And you see some points, the noise of the light goes below the standard noise, which is called shot noise. So this is a remarkable feature that the squeeze light demonstrates, and this is actually measurable in the laboratory. And I was so passionate to see the evidence of the quantum mechanics, and this is the first thing I've ever experienced that quantum is real. You may object to me, so still, basically, it is a hypothesis, so we call quantum postulates. So there are 4 quantum postulates, but these evidences basically support that those hypotheses are probably true. Okay, so then what are the applications of the squeeze light? So one of the kind of most hyped application was LIGO and measuring the gravitational field. So basic idea is very simple. So you have a very gigantic lag for Michelson interferometer. And if there is some kind of a shaking in the space through the gravitational wave, then you will measure some photon in the dark port. Whereas if there is no wave or anything like that, then you don't measure anything. So now squeeze light gives you some advantage because this is a measurement, and then again, squeeze light gives you less uncertainty and less variation in the measured quantity. So if you use the squeeze light, then you can have a better signal-to-noise ratio. And this is something I'm very passionate about, and Dell is working very hard for that. So basically, the idea is that Dell is interested in measuring the vibration of a membrane using some light. And then when the vibration makes a rotational movement, then he will get the non-trivial transverse mode. But when there is no vibration, then he will get only the trivial TM00 mode. And then if you use the squeeze light, then you can avoid two things. One, there is always light back action. So basically light kind of triggers the vibration. That's very bad. Number two, there is an uncertainty in the measurement. So if you use the squeeze light, you can avoid the back action and you can make an accurate measurement for the vibration. So Dell is working very hard for that. Another one is quantum imaging, which I will describe soon. So basically the idea is that you take the image and then compare with the two cases. One is use the classical imaging configuration and classical measurement versus use the quantum light and then quantum measurement. And the promise is that if you use the quantum light, then the imaging quality will be enhanced significantly. I will describe how later. And one another important application of the squeeze light is actually quantum computation. And this is called the cluster state, where two squeeze light is used to entangle every node of a two-dimensional state space. And basically what happens is that if you perform the beam splitter action on the two input states, which are squeezed together, then you can entangle multiple modes and then ever entangled and become now two-dimensional cluster state. What is the use of the cluster state? It's called the one-way measurement-based quantum computation, which is complementary to the gate-based quantum computation. And 2D cluster state is the resource to perform that one-way measurement-based quantum computation, which is exactly equivalent to the gate-based quantum computation. So especially 2D cluster state is very easy to make in optics. And then this promises the path forward to use the optics for quantum computation. Now, we live in an era of the AI, and one of the best use of the AI is to check whether you missed anything or not. So basically, the reason being is that AI is based on big data, and sometimes we miss things, whereas AI doesn't miss a thing because they rely on the big data. And then one of the best views is, again, to check if you miss something or not. So obviously, very similar to what I said earlier, like gravitational wave detection, quantum information and computation, and metrology and imaging. But these three I missed definitely. So quantum cryptography. So sometimes if you have a squeeze light, then it is difficult to beat the cryptography than using the classical light. And optical communication, yes, because if you use the phase shifting key, then phase measurement is the key for the success of the communication. And if you use the classical light, then there is a shot noise, whereas if you use the phase squeeze light, then phase measurement becomes much more accurate and signal-to-noise ratio becomes much higher. So yes, of course. And fundamental test of quantum mechanics. So basically, some people are thinking of using the squeeze light to test several things like Bell inequalities and stuff. So basically, the reason being is that squeeze light is also the source for entanglement, which I just showed earlier. And that's the major part of my talk, so how to use the squeeze light as an entangling resources. Okay, here is the generation of the squeeze light. So we typically rely on the Chi-2 process where you have a single photon coming into the material, and material interacts with the light in a way that the output becomes now split two photons, identical, which has half the energy compared to the pump photons in. And basically, the Hamiltonian to describe this Chi-2 is exactly like that. So in a second quantized formalism, you see that one photon is annihilated in the pump frequency, and then two signal photons are created and vice versa. So it is a reversible process. And then now, if you regard the pump as a very high power classical light, then now you end up with a squeezing operator. So basically, this is equivalent to squeezing operator, which creates the transformation. And basically, using this process, you can squeeze light. And in some sense, it is called the parametric amplification or phase-sensitive amplification. The reason being is that the amplification directly depends on your input phase. So when the input was 0 phase, then it is amplifying. When input was 90 degree, then it is de-amplifying. And it is called the phase-sensitive amplification. And as you can imagine, x-axis, q-axis is increasing and p-axis is decreasing. That's how you actually squeeze the light. And this is the one of the setup I use in Sandia. And it looks very simple, like it is just bow tie cavity, and blue is the pump, and then red is the signal. And this is only one part in million. So in actual squeeze light, you have a gazillion electronics running together around this small setup. And it's one of the most difficult experiments ever I did. Okay, now I'm going to describe some non-trivial action of the beam splitter. So basically, you are very familiar with beam splitters. So everyone is actually handling some kind of beam splitter every day. And I want to surprise you that beam splitter does an amazing thing that nobody expected before. Beam splitter is described by a very simple Hamiltonian called beam splitter Hamiltonian. And this is one of the quintessential quantum mechanics Hamiltonian you will ever use. So 90% of my work uses beam splitter Hamiltonian. And previous chi2 Hamiltonian is a variation of beam splitting Hamiltonian, except that you are now involving 3 waves instead of 2 waves. So beam splitter Hamiltonian, given that you solve for the Heisenberg equation for the annihilation operator, and you transform it, and then now what happens? What happens is that you have 2 input light. One is this way and another is this way. And you have also 2 output light. One is this way and the other is this way. So basically, you can view this as this light changes to this one, and this light changes to this one after some time. And that is described by actually the squeezing operator, beam splitting operator. And basically, the transformation after doing some algebra, very simple algebra using Bakers-Campbell-Hausdorff, then you end up with cosine and sine terms, and this is one of the most general form of the beam splitter transformation. And then now I like this particular example of theta becomes pi over 4, and phi becomes pi. This is the balanced beam splitter 50-50. And then now you end up with this nice transformation matrix. And then I can even reverse that to have a reverse relation between output and input. And then I'm now showcasing several things, amazing things. One, the first one is that I will put 1 photon into port 1 and vacuum into another port, and let's see what happens. So 1 photon can be described as a creation operator in 1, and that creation operator is combination of actually 2 modes after the beam splitter interaction because of this relation here. So basically, I take the dagger of this relation and then end up with A1 input becomes A1 output plus A2 output, and that's this one. And then let's calculate this, and then you end up with 1, 0 plus 0, 1 state. This is one of the Bell state. That is maximally entangled state, meaning that if you find 1 photon from this port, and you guarantee that there is no photon here, and vice versa, if you find 1 photon here, and there is no photon here. So this is maximally entangled quantum state, and this is very, very valuable quantum state. And what we did is just use the beam splitter with a single photon source. And that's how we created one of the valuable Bell state. And this is quantum entanglement. Next case, what about I put identical 1 photon here and 1 photon here? And then that state is described by two creation operators, A1 dagger and A2 dagger on the vacuum. And then again, going back here, A1 is combination of A1 plus A2, and A2 is combination of A1 and A2, but in the negative sign. And then after some algebra, using the commutator between A1 and A2, you end up with square and square, and this is 2, 0 plus 0, 2 superposition, which is very, very famous result called Hong-O-Mandel. So Hong-O-Mandel is coming from this very simple algebra from beam splitter, and basically it is describing that if you put one photon in, then there is no case where you get one photon out here, one photon out there, because of the quantum optics and the commutativity and so many things involved, like normalization and everything. But the end result is that, amazingly, there is no case where you get one photon out and one photon out there. So this is very, very striking and famous result in theory, and they actually proved experimentally that it's happening that way. So they never, any question?
Case 1, you have 1 over the square root 2 in front. Case 2, you have 1/2. What's happening to the normalization coefficient?
Exactly. Thank you very much. It's a mistake. So I was testing you to figure out or not. So thank you so much. Yeah. So basically, this should be so normalization factor should be corrected. Thank you.
But it's not so easy to get that normalization factor. In fact, it's not as straightforward as you have shown.
Yeah, but I must have done some stupid mistake somewhere. So basically, it's, for example, so A1 squared and A1 squared, and then there should be some, I'm sure. Can anyone find some stupid mistake here?
It's not a stupid mistake.
The coefficient that goes in front of the raising operator when you activate the ground state, you get the 2 factorial over the square root that should come out.
Here, 2, right? So, yeah. The 2. So anyway, so ask and so Brian knows that. So, right. Sorry about the mistake. All right. So now case 3 is the case where you put coherent state in one port and vacuum in another, and then the result is very simple. Like if you just describe the coherent state as a displaced vacuum, and then replace A1 using the combination of A1 and A2, then you end up with just nice split between port 1 output and port 2 output, and then they exactly split into half. So basically that agrees with the classical result. And there is no surprise because coherent state is more or less like a classical state. And this is actually the only case where trivial result of non-entanglement happens. Except for some very small subset of quantum state like here. I will explain later. And the next example is, how about I put a single squeeze light into here and vacuum there, and then the algebra shows that the squeezing splits into half, like here and there, but the squeezing stress becomes half compared to the original one. So it is less squeezed there and there. However, one more important thing is that there is a coupling term comes out. So basically, two-mode squeezing, this is called two-mode squeezing, very similar to single-mode squeezing, except that you have now different modes, 1 and 2. And then that is the source for quantum entanglement. So basically, what happens is that if you put the squeeze light in and vacuum, then you get the quantum entanglement, although that's not maximally entangled. But still, there is an entanglement. Now the next setup is most interesting. So if you put identical squeeze light in and here, then what happens is that amazingly, with this configuration, we don't see any squeeze light. So basically the input outputs are exactly identical. However, if you use the different beam splitter phase, meaning that this phase, I used a pi, phi equals pi, but if I choose different number, like for example, pi equals pi over 2, then basically what happens is that this, everything cancels out, the squeezing parameter cancels out, and then it leaves only the two-mode squeezing operator, which guarantees the maximally entangled output between two modes. So basically, depending on the beam splitter details, you can continuously change from non-entangled light to maximally entangled light. So that's very interesting state. Now, one of the interesting configuration is this particular one. So basically, you have a beam splitter array. So basically, the idea is that you split the squeeze light into two parts, and then you keep doing that until you end up with multiple output modes. And then basically, you can demonstrate that all the outputs are maximally entangled. And basically, this is the signature of the quantum entanglement. So basically, this concept I believe, was born in the professors of University of Arizona, and then this is now hot topic in quantum optics. So basically, most of the people are really thrilled to use this kind of a maximally entangled light generated from very simple configuration like single port squeeze light and multiple beam splitter array. So I am using this configuration to demonstrate super resolution imaging. Yeah, go ahead.
Is that what's used for one-way computing to generate like arbitrary unitaries, like detection, or that's not?
It's not it. So basically, the one that cluster state used is actually this example. So you need two squeeze light instead of single squeeze light, right? But this squeeze light has different applications. So it provides enormous advantage in terms of sensing and imaging. So no wonder some other people use this one. So basically, the idea is that, okay, how about we compare two cases? One, you use individual squeeze light on the sample, and it is called the distributed sensing because you have an identical object in many places, and you used independent squeeze light. That's case one, versus you use the entangled squeeze light. And then no wonder what happens is that the error of the measurement for the phase delay for the sample is calculated as 1 over n times square root of m. So basically here n is the number of photons and m is the number of modes. And if they are individual and not entangled, then there is a scaling of 1 over square root of m. And if they are entangled, there is a scale of 1 over m. So if the m number is very large, then the measurement error scales like dramatically differently. So basically, this was published in 2020, and many people got really interested, including University of Arizona team. And I also got interested, and my question was slightly different. So basically, I wanted to demonstrate some kind of a super resolution imaging, which is non-trivial because many people talked about reduction of the errors and noises and stuff like that, but how does it translate into the resolution, imaging resolution? That is non-trivial. So I did want to really find out the connection between the imaging resolution and the reduction of the noise. Okay, so now we need to talk about the imaging. So typically, the Rayleigh diffraction limit is the imaging resolution limit, which is typically explained by this way. So basically, when two light sources are within a distance called Rayleigh range, then it is very difficult to tell whether there are two sources or a single source. And the Rayleigh diffraction limit is related to the light wavelength and imaging details like lens focal length and lens diameter. And you do everything you can do, like best form lenses and immersive optics and everything. Still, if you use something like a 1 micrometer light wavelength, then it is extremely, extremely hard to go below 200 nanometer in terms of the imaging resolution. But I did some intellectual exercise and that demonstrated that if you use something like an 800 nanometer, then you can accomplish something like 40 nanometer resolution using quantum optics. So that's the result I'm going to show you later. So I'm going to explain the 4F system, which is the typical imaging system we always have. And the reason why this object cannot be exactly reproduced in the imaging plane, which is actually measured, is because of the fact that the lens has only the finite aperture, meaning that some information is lost outside the aperture size, which is now currently modeled as an aperture, really hard aperture in the middle. And as a result, what happens is that this Fourier domain loses all the higher frequency, spatial higher frequency components. That's why it is so blurry like that. Now, in principle, what happens is that, okay, you can actually come back here by measuring this one very, very accurately, and then now see if there is a hard cut or something. And then because in principle what happens is this. So original function was analytical, and then you are putting a hard limit here and there. So if you examine the part in the middle very, very carefully, then you can actually extrapolate this part into the outside part by doing some kind of something like analysis. And then in the easiest analysis is Taylor series. So start from anywhere, and then you can actually go everywhere and then retrieve the lost information. The problem of doing that is the noise. If the measurement is noisy, then that extrapolation will be really outstretched, and the retrieved information will never be accurate. So now, in that paradigm, what matters is, can you reduce the noise in the imaging plane? Yes, that's the point where the squeeze light comes in. So if you use the squeeze light, then you can drastically reduce the noise in the imaging plane. So for that, I want to introduce some kind of transformation between these two planes, and this is called the Splanian transformation, called after the person called Splanian in Bell Labs. And basically, the idea is that you want to decompose your image into the series of the orthogonal functions, and then you want to identify accurately the coefficient of each function and then add them together to retrieve that. So that's my idea, to retrieve the original object. And then for that, I expand the original object into the superposition of many bases. And these bases are called prolate spheroidal wave functions, sometimes called Splanian. And it is based on the wonderful characteristic of that this function is the eigenfunction of that Splanian transformation. So basically, if you put the Splanian function in, then you get the Splanian function out with some coefficient in front. And then I don't want to go deeper into all the math derivation, but basically what happens is that I want to reproduce the object using the measured data at the imaging plane. And in this particular case, I make an example of the phase distribution, but you can actually perform the amplitude distribution as well. So basically what happens is that I want to use each light coming from this beam splitter array, and then now measure one by one at the imaging plane, and then now reconstruct the original distribution of the phase in space. And this is the result of something like, 30 lines of the derivation. And then basically what happens is that it contains many things, including the measurement. So the measurement is decomposed into the orthogonal series with the coefficient, and that coefficient is used here. And then this is the superposition of the many Splanian functions with some designated coefficient rule that now includes important parameters like original squeeze light displacement, alpha E, and original the number of entangled mode. So basically here, the squeeze light has alpha E displacement, and there are m number of entangled lights. So basically this is the rule to reconstruct the object. And based on that reconstruction rule, I can actually calculate what is the imaging noise. And this is the result of calculating the imaging noise. And imaging noise contains many things. And then what happens is that typically you want to optimize everything in a constraint where the number of photons hitting your object is limited. The reason being is that you are interested in, for example, bioimaging, or you are interested in Dell's experiment where the back action matters, then you want to really limit the number of photons hitting the sample. In bioimaging, for example, you don't want to destroy the viruses or something like that. And then the constraint is that you want to really limit the number of photons hitting the sample. And in this particular case, the formalism is the Lagrangian multiplication method. And then basically the solution for this optimization gives me the optimal imaging noise now that demonstrate so-called Heisenberg limit. So you know that in statistics, if they are not correlated, then the error scales like 1 over square root of n. Here n is trial number. But in quantum, what we always promise that you can turn 1 over square root of n error scaling into 1 over n if you use entanglement or some non-trivial quantum feature. And deriving that is a big deal. And basically, in my attempt, I successfully derived that the imaging noise after the optimization demonstrates Heisenberg limit for both the number of photons hitting the sample and the number of entangled mode M. So basically, using that result, you can actually demonstrate the super resolution imaging. But how? The question is that, okay, so reducing the error is one thing, but how do you prove that the imaging resolution is improved? Here is the connection between the error and the imaging resolution. So basically, imaging resolution is how many lobes you can see under the sample size. So basically, if you look at the Splanian function, then lowest mode has less number of lobes, and higher order has higher number of oscillations. And basically counting each number of lobes, then you can see between the size, which is -1 to 1, you see that the number of lobes is like a q plus 1 here. Q is the highest order of Splanian function you used. And if you successfully retrieved qth order Splanian coefficient, then the imaging resolution is more or less like the object size divided by q plus 1, because of the fact that your highest order, reliable highest order retrieval has q plus 1 oscillations within the object size. And then basically the question is then how to determine the highest order q. The idea is that if the measurement is noisy, then convoluting the higher order modes of Splanian with noisy data will give you garbage coefficient. So that's the Fourier transform. And then you have to really cut the highest order of number q at some point where your information is reliable. So you cannot really arbitrarily go to higher and higher orders, but you have to use a certain limit q. And the rationale to cut q is typical rationale we use all the time. So signal to noise ratio 1. And then this is the criteria to find the maximum q that is reliable. So using this formalism, I can actually demonstrate that the noise of my method scales like 1 over n times m. Here, n is the number of photons hitting the sample. M is the number of entangled mode. And then now, if you use the non-entangled squeeze mode, just like the Nature paper, then you can demonstrate that actually you can calculate that the imaging noise scales like 1 over n times square root of n. Still, you demonstrate 1 over n Heisenberg limit because of the fact that the light is squeezed. But if you now use the classical light, which is the coherent light and non-entangled, then the calculation result is just a standard limit, 1 over square root of n times 1 over square root of n. So now, this is the one numerical example that I want to show you. So basically what happens is that the goal of this imaging retrieval is to reproduce the original object, which is quite complex. And the size here is about 300 nanometers. So I'm using something like 800 nanometer light. And the Rayleigh limit is about 200 nanometer. And then now you see comparison of the retrieval from the classical light, which is this line, and quantum imaging, which is this line. So if you compare these two results, then you will see the quantum has much more detailed retrieval compared to the classical one. So basically, the idea is that you use one single squeeze light and then create multiple entangled light through the beam splitter network, and then use your sample and use the homodyne and pixelated homodyne, and then retrieve the original one using some software method. Currently, Dell's group uses hardware method, but this one uses software method. Yeah.
Can you re-articulate what you mean by the modes that are being entangled in the illumination?
Yeah.
Of this object?
Right. So basically, going back here, so the mode that I'm using is actually the individual mode one at a time, right? So basically, I'm using this mode to do the imaging, and next, I'm using this mode to do the imaging, and so forth. So how many times I repeat that? So basically, that's the number of modes.
So do you use the time beam at the mode?
Yes, exactly. So there is a time delay between the modes, and then I do the imaging one at a time. Yes. Thank you for great questions. All right, so basically, yeah.
So if you go back, you're showing this in one dimension.
Yes.
Is it a one-dimensional mathematical system or is it two-dimensional?
This example is one-dimensional example. So
What's forming the mathematics? Just like a square? So it's a two-dimensional optical system with one-dimensional limit?
this formalism is just a one-dimensional calculation, but you can expand to two-dimensional calculation.
So this is real or this is calculated?
This is calculated. So yeah, I was not really clear about that. Sorry about that. Yeah, go ahead.
Daniel, on your plot there,
Yes.
we can't really see how severe the error is
Okay.
at the boundaries because it looks like it just goes to infinity.
All right.
Is that a really humongous error?
No. So what happens is that you are going to take only the data between -1 to 1, because that's the aperture, valid aperture for your object. So this error after -1 and then after 1 doesn't count, right? So we are integrating the error only between this window, because we know that the object size is -1 to 1. So.
That means you know the object.
No. I know the mathematics of my optics, and then I have a good idea what is the view area of my imaging. That's what I mean, right? Okay. Actually, the object may be much smaller than this, right? So, yeah. Go ahead.
So you're using the homodyne because you want to measure the phase, not the
Correct.
amplitude?
Correct.
But if you were doing the same procedure on amplitude, it would have been fine.
Yeah. So if you are interested in amplitude instead of the phase, then you have to squeeze the amplitude squeeze light, and then use it. Yeah. And then use the homodyne for measuring amplitude instead of the phase. Yeah, correct.
What is the space bound product that you're doing?
Space.
The Shannon number, like how many modes?
Oh, yeah. So this is only 6 modes here, right? Yeah. Any more questions? Okay, thank you. So now, future direction is obviously, like you said, we want to expand into 2D, which is trivial, actually, because there is a 2D splenium function, whereas I use 1D splenium function. So basically, the purpose of this exercise is to demonstrate the performance of quantum optics, and then therefore, I just used 1D for simplicity, but expand to 2D. Now, what is non-trivial is 3D. So basically, how do you actually expand into 3D? Because bioimaging requires 3D, and that requires tomography. So basically, what is interesting is really 3D expansion. And then, so the grand goal is to actually non-intrusive real-time bioimaging. And this needs an efficient machine learning, because you need a lot of calculation. And then we discussed with Dell, and Dell uses hardware which is fast, and I use the software which might be slow. So basically, it requires machine learning. And one day, I hope that we can provide a video streaming of actual bioactions at nanoscale using visible or benign infrared light. So that is the goal. So second part is now single photon counting. I will spend less time than that. So basically, I just jump into ChatGPT. So what is the use of single photon counting in gigahertz photon? Obviously, ChatGPT gave me some vague, ambiguous answer. So I can understand quantum computing with superconductor qubits, yes. If you have a single photon, then single photon counting detectors, then you can analyze the quantum state and then do the tomography of the quantum state in superconducting qubits. That's great. Quantum electrodynamic circuitry, yes. But quantum communication at gigahertz photon, I'm not so familiar, but it picked up somewhere, definitely. But that it will be very inefficient because of the bandwidth limit and everything. And fundamental physics, I'm not really sure what it means. So, yeah, there is a meteorology and astronomy. But what matters is actually why do we care as a university entity? So this is real reason, actually, why the gigahertz single photon detectors are really useful for us. So basically, Matt Eichenfield is developing no-stop the phonon quantum computation because he loves phonon over photons. And basically, the idea is that you can convert back and forth freely between the gigahertz photon and gigahertz phonons. And then if you have a phonon qubit, then it will be relatively easy to convert back into gigahertz photon and use the photon detector. So that is the actual motivation to have a gigahertz photon detector. And then now, a good thing about this is that the phonon can be converted into photon using optomechanical system. So Dell knows very well, and Matt Eichenfield is the world expert for that. And phonon qubit seems to be quite promising and very exciting. Obviously, there are other applications, real applications like astronomy. And this is called scanning acoustic microscopy. The trouble with the SAM today is that the resolution, the signal-to-noise ratio is so bad because there is no single photon detector or anything like that. So if we have a single photon detector at gigahertz, then we can convert the phonons into photons and then use such detectors. So that's the real one. Now, one more important thing about this utility of the gigahertz photon detector is the typical way of reading superconductor qubit today. So this is the state of the art. So suppose that you have a qubit, then what happens is that you kind of bounce off your input light, which is very, very small photon. And then now the output of your input bouncing back from the qubit has two possibilities. So if the qubit is 0, then it shifts positive phase. If the qubit is 1, then it shifts to negative phase. And then this is too much noise, and then you don't like it. And what you do is that you amplify this and through several stages, and then actually 4 stages later. And then you finally get the final output reading the homodyne of this setup. So this is really too much involved. What if you just remove everything and just put the single photon detector at gigahertz? So basically that is the impact of this work. So we all use semiconductor for photon detectors, and the trouble of doing that is that we cannot easily find the semiconductor that observes a gigahertz energy. So that energy is so small. What about using graphene that has a Dirac cone? And yes, in principle, you can do that. But, okay, so there are even papers that uses graphene for single photon detection at gigahertz frequency. However, extremely difficult to extract the Joule heat. So basically, the idea is that you wait until the photon absorption is dissipated through the phonons, and then you measure the Joule heat of the graphene, which is only single atom layer, which is extremely hard. And also, it is extremely hard to manufacture in scale. So currently, graphene is still doing like Scotch tape, and it's extremely difficult to port that Scotch taped graphene onto the position you want. And yeah, there are natural defects, and then there is some impurities that prevents this kind of Fermi level sitting exactly at the middle, and that will be disaster for your detector. So now, alternative idea is, we thought, and how about topological material? So topological material naturally does that. So surface of the topological material provides graphene-like Dirac cone that can be used as a photon absorber for gigahertz photons, and the bulk can be used as a detector. So basically the idea is that the surface of the photon transfers its decay energy to the phonon of the bulk, and we are going to measure how much temperature elevated in the bulk by measuring actually the resistance of the bulk. When the bulk becomes superconductor, then there is a critical temperature where slight change in the temperature increases the resistance dramatically, and we are using that thing. So it is called a edge detector. So basically, we rely upon the edge detection technique, but importantly, topological material provides graphene-like photon absorber without too much hassle. So basically, we calculated all the details, like how much energy is transferred to what, and then basically we end up with the calculation that, okay, so with a certain dimension of the device, then we can expect something like, for single photon absorption using topological material, we can expect something like 2 to 10 micro-ohm increase in the resistance of the superconducting bulk, which is very hard, but it is possible. What is even better is, how about we use a nanowire, because the heat capacity of the nanowire is much smaller, so temperature will increase dramatically. Only difficulty is that we have to use something called Majorana zero mode, which is Majorana particle, which was not proven to exist yet. So basically, that is the only hurdle we have to overcome. And then it was expected that our manuscript will be rejected because we are using something that doesn't exist. Fortunately, the reviewers were very sympathetic, so we succeeded in publishing this amazing paper that uses the Majorana particle to improve the photon detector at gigahertz. So compared to the micro-ohm increase, you now see kilo-ohm increase. And then basically, I don't want to go very deep into this material, but basically it utilizes the Majorana zero mode coming from Rashba spin orbit locking. If it doesn't make any sense, that's fine. So what matters is basically we use the nanowire as a detector, and the heat conveyed to nanowire causes a lot of temperature. I mean, the temperature increase, therefore the resistance increase. Because it's nanowire, the resistance increase too. So it's double effect. So yeah, and this is my final slide. So basically, we are working hard to really demonstrate real intelligence. So what is real intelligence? True intelligence finds breakthrough with insufficient data points. So anything depending on big data is not actually a true intelligence. So we want to really do the true intelligence, and we are pursuing true intelligence based on very scarce data points and really use amazing human mind. That's what we do. And obviously, all our scientific knowledge is tentative, so we don't really take everything granted, and we challenge the even established facts and all that. So basically, we are interested in demonstrating several things like cluster states, anion physics based on the topological materials, and non-trivial quantum materials. We are also interested in quantum transduction and connected quantum system, which I gave a talk about. And then now the real big deal goes here. So basically what happens is that everybody now got so much frustrated that error correction will not happen in scale. And what do we do with the intermediate, noisy intermediate scale quantum? The best usage, I think, about the NISC is to build a learning machine. So quantum learning machine makes sense because the connecting quantum system together exponentially increases the degree of freedom compared to the classical system, and then we can dramatically reduce the resources and energy to perform a computation in the quantum system. So that's our dream. And our postdoc, Peter Ellis, is working very hard for that. And he even demonstrated some theory result today. So I'm very happy about it. So thank you for your attention.
Any questions?
Can you go back to your slide and talk about the sampling on Z?
Sampling, but
Along Z?
sampling along Z. Okay, yeah. So the imaging, right? So which slide do you want?
I think it was the last slide.
Last slide, okay. This one.
Sure. I guess classically, when we want to expand the spatial resolution,
Mm-hmm.
we increase the aperture size.
Yes.
And as a consequence, we get a very short depth of field.
Correct. Yeah.
And so maybe that's not a Z
Right.
resolution, but more of a drop-off in
Right.
spatial resolution.
Yeah.
So in your case, because you're super resolving beyond the diffraction,
Mhm.
when you actually recover the image, do you see a narrower depth of field?
Yeah, so what happens is that if you don't perform the retrieval of the lost information, then you will have to live with the Rayleigh diffraction limit all the time. So there is no way around. But in this scheme, we introduce the retrieval of the lost information by going backward and then recalculating the lost information after averaging out the measurements so many times. So basically, this is somewhat different from conventional imaging that doesn't do the retrieval of the lost information.
So it does appear like a narrower depth of field.
Yes, correct. Yeah.
I'm kind of surprised in this analysis that you're emphasizing the increase in the modal throughput as opposed to just the error reduction in the modes that you're getting. Like, you know, resolution can be defined many, many ways.
Yes, correct.
But here, like even if you don't increase the modal throughput, I mean, actually, in this kind of system, as the Shannon number gets large, increasing the modal throughput is very, very difficult. It wouldn't really matter what your noise is.
Correct. Yes.
So but you can improve resolution just by better SNR on the modes that you get.
Yeah.
How did you choose this kind of measure for resolution?
Yeah. So basically, the resolution measure we chose is not coming from ours, and it's coming from literature. So basically, that's the. So this famous paper I cited earlier. So right. So yeah, this is quite well-known paper about the quantum optics and the squeeze light imaging particularly, and they happen to choose the resolution definition like that. But I am open to adopting new definition of the resolution. Yes,
Because if you just chose like the Rayleigh criterion, then it would be very easy to say
Right.
that you get the 1/n instead of 1/square root.
Yeah, potentially. Yeah, but there is a always nonlinear relation between the imaging noise, accumulated noise versus the resolution. So
I guess the difference is usually between like choosing a parameter estimation versus choosing like nodal estimation.
Exactly, correct.
Parameter estimation,
Yeah.
you probably would do better.
yeah, correct. Yeah, thank you.
And it's more of a clarification. Go to the setup, the simulation setup where you have the multimode entangled light. Just wanted to,
This one?
No, actually, where you showed the resolution improvement. It showed the system and the homodynamic detection. Yeah.
Yeah.
So in this one, seems like you need this homodynamic detector, right? Spatially resolved. So right now you're scanning it, I guess.
Correct.
You have the
Yeah. Correct.
the time.
Correct.
But as you extend it to 2D, then you have to scan through all of those. So
Correct.
is there a equivalent, I guess, homodynamic detector that
Right.
one could envision building and have an array of it, right? Because that will eventually lead to loss of
Correct.
scaling, right?
Yeah.
I mean, I guess
Correct.
confocal does it by scanning,
Yeah,
but it has the same issues of
Yeah.
scanning, real time.
you're right, Ashok. So basically, that's a good point. So basically, you need a pixelated homodyne, and that will kind of increase the performance dramatically. Yes, correct.
But you still have to switch through the M entangled modes, right?
Yeah, that's right.
And is that what is showing up in the number of photons? It's 50 times 50,000, so that's 50 entangled modes you're simulating?
No, it is not related there. So it is something different. So yeah, it is somewhat subtle. Yeah. I don't want to spend too much
Do
time.
you need a pixelated detector, or can you just scan a single mode detector?
You can scan like this. So basically, this is a single mode detector, but aperture scans. You can do that, or for the speed, like Asha suggested, you need a pixelator for the speed. Yeah.
I think I didn't understand how you actually switch from one B1 to B2.
Oh yeah. Okay. So
How is it done?
yeah. So the person who asked, I'm sorry, I didn't hear the name, but basically the way is that okay. So where is the picture? Okay. So here, yeah. So basically, you have a time delay for each one. So basically, I used in paper the fiber time delay, and basically you put a shorter fiber here, slightly longer fiber, and then longer fiber and the longest fiber here. So that will delay the time, and then you have a switch, optical switch here, and then that will select each mode, right? So that is the depiction of mode selection, but we have much better now choice with the where it's at. Yeah, so basically we can choose different mode in real time much faster than this.
One quick question. Thank you for the talk, by the way. So you had mentioned earlier that the problem with doing continuation, if I understood this correctly, like when you're discussing the Rayleigh diffraction limit, the problem with actually like deconvolving with, say, a known PSF, is that the actual noise in the measurement causes issues when you try to extrapolate outside of, say, the frequency bandwidth, the spatial frequency bandwidth that you're seeing.
Right.
So what I'm wondering is, when you inject, say, squeezed light to the image or sample, are you trying to reduce the noise along like a certain quadrature that allows you to do this, what do you call it, continuation even like a little bit further out? So.
Okay. So I understand your question, and I have a better answer than directly answering your question. But basically, to answer your question, yes. So basically, the idea is that we are going to use the squeeze light only inside the aperture, right? So outside the aperture, we still have shot noise, and that actually contaminates the measurement too. So basically, this lens accepts the outside that is not squeezed, and what we do is only partial. So in order to really enhance everything, you have to really somehow provide the squeezed vacuum outside. That will reduce the measurement noise much further. So that's a good point. And basically, the reason why I said I can give you better. So basically, here. So this is the out-pupil orthogonal series that is currently not squeezed. So basically, if we replace somehow this one with the squeeze light, then everything goes really smooth, and then you can accomplish much better result. And only thing is that we don't know how to put the squeeze light outside the pupil yet. So yeah, all right.
Any more questions?
I'm sorry, why can't you put it outside the pupil?
Because it's blocked here. Right. So somehow you have to pass through this blocking.
So you couldn't do a synthetic aperture there?
Probably synthetic aperture is the answer. Yeah, potentially, yeah, that's right.
All right, let's thank our speaker.